aspartate, and glutamate. Okay, the 7 here. So the 7 amino acid, the side change and change of according to the pH can have several charge, different charge. So you have also the PI, so isoelectric point. We will see how to measure it. And also you have the hydropathy index. So hydropathy index measure the free energy of transfer of the residue from hydrophobic solvent to water. It means that more positive number here, so more positive number here, more indicate more hydrophobic groups, and more negative value here indicate more hydrophobic air group. Okay, so that's why the charged amino acid has negative value, because these amino acids are hydrophilic, and with the side chain, which are composed only with carbon and hydrogen, you have positive value because they are hydrophobic. And sorry, the last column corresponds to their occurrence in proteins. Okay. So each amino acid has a specific isoelectric point, PI. So according to the pH, each amino acid can have several charge, okay? And we can separate the amino acid according to the pH and according to the charge of the amino acid, okay? So the overall charge of amino acid depends on the pH buffer, okay? When the pH is higher than the PI, in this case, the amino acid is negatively charged, so it will migrate to the positive electrode. When the pH is lower than the PI, the amino acid is positively charged and it migrates to the negative electrode. And when the pH is equal to the PI, it means that the amino acid is neutral and it does not migrate, it stays at the same place. Okay, so for the electrophoresis, what is the principle? You have support, which is paper, cellulose, silice. If you can depose your sample, the mixture of amino acid, and this amino acid will migrate under an electric field, okay, according to the charge of the amino acid. At the end of the electrophoresis experiment, you can detect the amino acid by hydrine. It's a compound which can react with the amino group of the amino acid, and it's become purple. Okay, so we can detect at the end of the experiment where are our amino acid. Okay. I have one more slide, and after we can make a coffee break. Okay. So here, how can we calculate the isoelectric point of an amino acid? For example, when you have air side, the side change, which is neutral, which cannot be protonate or deprotonate, you have only two pKa value, So it's very simple. So pi is the average of this pKa value. So pKa1 plus pKa2 divided by 2. It's more complicated with a side change, which can be protonate or not. Okay. So, for example, here you have histidine. The pKa1 is related to the carboxylate group. pKa3 is related to this function, and pKa2 is related to the amine group. Okay? So, if we draw a diagram according to the pH, at low pH, all the functions are protonate. Sorry. COOH, Na3 plus, and the ring is protonate. When we increase the pH here, when the pH is higher than the pKa1, the function related to this pKa1 will be deprotonate, so the COOH becomes COO minus. When we increase the pH, this ring becomes neutral because it's pKa3, it's related to this function. And when the pH crosses the pK2, the amine group become neutral. It lost its proton. Okay? So where is the neutral form? The neutral form, here you have 2 positively charged, here 1 positive, and here you have the neutral form. Okay? So the pi of histidine is the average of the pKa, but this time it would be pKa3 and pKa2. It means it's the average of the 2 pKa which surround the neutral form. pK2, pKa3 over 2. Understood? In the same way, I plot the pH diagram with all the charge of arginine this time. Okay, so you have the arginine form at acid media and arginine form in the basic media, and the neutral form of arginine. This is it's neutral. So the pi of arginine will be the average between the 2 pKa which surround the neutral form of the amino acid pKa2 neutral form. Okay, we will have an exercise on this. Okay, so I told you that peptide and protein are polymer of amino acid linked by a peptidic bond. So a peptidic bond is a covalent bond. The covalent bond between the carboxylate group and the amino groups. It's not spontaneous, and it forms, so it means that it's not thermodynamic favorable and formed during it's formed in the body during the translation of in the ribosome. A water molecule is released and it's absorbed around 210 nanometer. The fundamental properties of the peptide bond, it's planar. It means that the 2C carbon alpha, the oxygen, all these atoms are in the same plane, okay? So you have 1, 2, 3, 4, 5, 6 atoms in the same plane. It's very important. We will see that after. And you have the length in angstrom of the bond. So a series of amino acids joined by peptide bond form a polypeptide chain, and each amino acid unit in a polypeptide is called residue or amino acid. Okay. Very important thing, a polypeptide chain has polarity because its ends are different to its beginning. So it's a convention, but we always start to give the first amino acid when we call a peptide correspond to the end side. So here you have the end side. So it's also called amino terminal residue. And the last residue called the C side, the carboxyl terminal residue. Okay, so tyrosine, glycine, glycine, phenyl, leucine. It means that tyrosine is the first amino acid in the end side. You have the end side of the tyrosine here, and you have the C side, the carboxyl group of the leucine here. It's very important because if we call leucine, phenylalanine, glycine, glycine, tyrosine, it's not the same polypeptide chain. Okay. Okay. And we will see that some peptides have biological function, and we will talk about the isoelectric point of the peptide in the second lesson. Okay. So if you have any question or not.
So can you send the slide for us and textbook? Sure. Because a lot of things we forgot a lot, so we need to read again.
Sure, and I will send you all the slides and by email if you have an email. I know you have an email, but usually you have a common email for all the students.
Yes, we have.
I will ask Han. Okay. Don't worry, I will send you the slide. Sure. So we can have. You have a chat. Thank you. Okay. I have the email. We can have a coffee, maybe a tea break for you because it's the afternoon. And after we can make some exercise online and exercise. Okay. So let's have 10 or 15 minutes. That's okay?
Okay.
Okay. See you. Ah non. Je me dis pourquoi c'est pas. Ouais. Ça marche. Okay, this molecule can be protonate, okay, to give the conjugate acid, which is called 3H+. Okay, so this molecule is tris, and this molecule is tris H plus. So you have to explain how to prepare 100 milliliter of this buffer at this concentration and at this pH. So I prepare 1 knot. 5 2 okay. Okay, you can see my screen, it's okay?
Yes.
Yes, okay. Okay, so this I already write in the slide, so it's okay. So how to prepare one uh, 100 milliliter of twist buffer. So you have the concentration here of the buffer and the pH. Okay, the concentration of the buffer, it means that this is the total concentration. It means that tris plus tris H plus, it's equal to 0.1 mole by liter. Okay, and I told you that we need the Anderson equation. So remind you, it's pH equal pKa plus log the base form over the acid form. Okay, so from this equation you can obtain the ratio between tris and tris H plus, because you have the pKa, which is 8.1. You have the pH, which is 7.9. Okay, so the ratio between tris and tris H plus, it's 10 power pH minus pKa. Okay, so you have to calculate this, and because you have two equations with two unknown, you can calculate tris H plus, the concentration of 3S plus and tris. Okay, can you do that? Tell me when you have the answer. Tell me if you need more explanation or you didn't understand what I told you. Do you have the answer? Do you try?
Is the answer for the concentration of T8 plus is 0.0613?
Okay,
And
0.061.
3.
So,
Yeah.
okay, see if you need the 3.
And
No problem.
the second one is 0.387.
387.
Yeah, 38, not 37.
Sorry. Okay? Okay, everyone? So,
Yes.
okay, perfect. So, to prepare a trace buffer, we need trace, which is a solid. So, the mass of the trace you need, it will be the total concentration of your buffer, the volume of your solution, and the molecular mass of the molecule. Okay? So, if we calculate this, it will be 1.21 grams of trace. Okay? You will put your trace in a solution in water, and at the beginning you will have 0.1 in concentration of trace, and you will add chloride acid. Okay, so we need the volume of chloride acid you will add to obtain at the end the concentration we did calculate. So at the end, we know that we need 0.0387 of trace and 0.0613 of trace H plus. Okay, so what is here? The concentration of chloride acid that we need to put. Okay, it's if you want to have this concentration, you have to put 0.0613 mole per liter of chloride acid, right? Is it okay for you? Indeed, you have a total reaction. So all the acid you put will react with the trace, and this concentration, I will put another color, it corresponds to 0.1 minus X. This. Okay? And all the acid that react with the tris. For the acid here, it will be 0. And here, all the acid which react with the tris will give the tris H plus. So it would be X here. It's okay for you? Long time ago, you did chemistry, right? I hope. Okay. So the concentration of fluoride acid will be this. So the volume that you need to add, it's the number of mole over the concentration. Okay, so it will give 6.13 milliliter. Is it okay? Try to do it again without the correction, because I always ask during the exam how to prepare a buffer solution. Okay.
Can you explain again why that form treat blood is the acid, the hydrochloric, and then we can find the X only by that equation? I still don't understand.
Okay. I will remove that. Okay. So at the beginning, in the initial state, you have 0.1 mole per liter of tris. This is because you have weighed the mass of tris and you put it in the water. Okay? And after, we wonder how many chloride acid we have to put to obtain our buffer at this pH. Okay? And at this pH, at 7.9, we had calculate the tris concentration in the buffer. So this is at the final state, when the reaction had finished. You should have at the end 0.0613 of tris H plus and 0.0367, right? But because you have a total reaction, all the acid that you put will react with the tris. So the tris concentration will be 0.1 minus X. You will have not any more chloride acid at the end, and all the acid which react with the tris become tris H plus, becomes X. Okay? Because you have a total reaction. So now we see that the X corresponds to the concentration we want for the tris H plus. So the X corresponds to 0.0613 mole per liter. Is that okay? But I hope it would be okay. If you want, I can give you some exercise to practice. Do you have any other question? I can move on the next slide. Oh, please. So we will see in this question how it is very important to use buffer solution when we do enzymatic reaction, for example. So here we have an enzyme and its substrate were solubilized in the buffer we prepared, and the substrate transformation generates 10 minus 2 mole per liter of proton. So we need to calculate the pH at the end of this reaction. So what happened? You always have this reaction, tris plus H plus give tris H plus. Okay? At the beginning of this reaction, at the initial state, you have 0.0387 and 0.0613. This is the initial concentration of the buffer, right? We told you that this transformation generates 0.01 mole, 10 minus 2, so it means 0.01 mole of H plus proton. Okay? So at the final state, at the end of this reaction, all the acid will react with the tris. So it will be at the end 0. So we put 0.03787 minus 0.01. So it will be 0.287. Here all the protons are hard react, so there's no more proton. And all the acid becomes the tris H plus. So it's 0.07313. Okay? So we have the final concentration of each component of the buffer, tris and tris H plus. We can use the Anderson, so the new pH value. We can use the Anderson equation, which is pKa plus log of tris over tris H plus. So it's 0.1 plus log of 0.0278. Okay, so give me the value of this.
Is it 7.7?
7.771. This is because I can hear you. It's okay?
Yeah.
Okay.
0.704, so
04. Let's write 04 as you. Okay. So you see that when you have an enzymatic reaction, the pH remains quite the same value. Okay, we start at 7.9 and at the end of the reaction it's 7.7. Okay, and 10 minus 2 mole per liter is a very high amount of proton. Okay, so usually you don't have this. And we compare, so this is the first. When we compare this value to the pH value from in the reaction, so when it occurs in water, the final concentration of proton will be 10 minus 2 mole per liter. And so we can use this equation. pH is minus log of H plus. So it will be 2. So you see, if we did the enzymatic reaction in water, you will decrease the pH from 7.9 to 2. And if this reaction occurs in the buffer solution, the pH remain quite similar. That's why we need always, with biological reaction, a pH, a buffer. Okay? Okay. Second exercise, except if you have question about the first. No. So
I missed the last part.
yes,
Yeah, give me a second.
the second. Yeah,
I need no. The next one. This
this one.
Yes.
What is your question? No, you want to write.
Yes.
Okay. Tell me when you finish.
Okay, I'm done. Thank you.
Perfect. I will give you also this this file. Don't worry, but it's okay. Okay. Now we have a mixture of 4 amino acids, so glutamic acid, glycine, histidine, and lysine, and we want to separate them using paper electrophoresis. So, in the first question, we have to define and calculate the isoelectric point. So, define, know now the isoelectric point corresponds to the pH. The pH when the amino acid is neutral. Okay, so for this we have to draw. I will draw the pH diagram, and I will plot. So, for example, I'll start with glycine, which is the most simple amino acid. I have 2 pKa, okay? pKa 1 and pKa 2. So, with this amino acid, it's very simple. So, I will draw.
Chị phải đến 5 rưỡi tiếng là sao? Mình nhắn thì không phải. Rồi đi xong rồi
So, at low pH in acid media, you have all the functions which are protonate. So the acid is neutral, COOH, and the amine is positively charged. So when the pH increases and the pH is higher than the pKa, you start to deprotonate. The pKa1 corresponds to the pKa of this function. You start to deprotonate this function. Okay? And after, when the pH is higher and pKa 2, pKa2 correspond to the pKa of this function, it means that you will deprotonate this function. And so you have the neutral form, it's here. It's the deuterium. So the Pi of lysine, it's the pKa1 minus pKa2 over 2. And its value is 6.07. Okay?
Okay.
Okay. For histidine, I did it during the class. Okay, if you remember that, I had to in this, and the Pi of histidine will be the average of pKa1, 2, and pKa3. Okay? So, I will do for lysine, for example. So for the lysine, I draw also the pH. So I will put the histidine. Histidine, we said that it was pKa2 plus pKa3 over 2, and it's equal to 7.669. Okay. Here, for lysine, we have 2 pKa, 3 pKa. So pKa1, pKa2, and pKa3. Okay? I can draw the amino acid formula. So, sorry, at the beginning, at low pH, all the functions are protonate. So the amide group are protonate, the carboxylate group are neutral. The first pKa corresponds to this function, so I will deprotonate this function. The pKa2 corresponds to this function. So I will deprotonate this. And the last one. The last one corresponds to this. Oh, sorry. So it will be neutral. Okay, so the neutral form is this here. So for lysine, the Pi will be the average of pKa2 plus pKa3. Would be the average between these two pKa. So it will be 9.8. Last example, I hope you will understand with the last example if you did not. So the pH for glutamine, So you have 3 pKa. So we have to order the pKa value. So the first one is pKa 1. The second one at 4 it's pKa 3. So and pKa 2. At the beginning, all the functions are photonate. pK1 corresponds to this function. So at the protonate, this function. pKa3 correspond at this function as the carboxylate group of the side chain. So I deprotonate it, become minus, negatively charged. And the last one, this one, correspond to the amine. So I will have these molecules. Okay, so the neutral form of glutamate, it is here. So the pi, it will be the average of pKa1 and pKa3. So it's 3.09. Do you have any question? Is it clear?
Yes, it's clear.
Okay. So, the last question. So the experiment, we did 3 type of experiment at 3 pH value, 3 different pH value, 1, 7, and 11. Okay. So for each experiment, we have to say how does migrate the amino acid. How, sorry. P. Inside. Est-ce qu'on peut faire ça? Non, maybe too small. Sorry, I forgot to copy that. Okay, so the, is it too small, the police, or maybe I can increase it? Okay, so we did the experiment at 3 pH, 1, 7, and 12. So write the line formula of the predominant species of each amino acid at this pH. How does it migrate the amino acid, and where should be deposed the mixture at the beginning? Okay, so let's see what I wrote. So I will do that for at pH 7, and as homework you will do that at pH 1 and 12. Okay, I will explain you at pH 7. So at pH 7, so glycine at pH 7, okay. pH 7, it's here, okay, pH 7. So glycine, it's neutral. Lysine at pH 7, it's here. So it means that lysine will be positively charged. Glutamate, pH 7, it's here. So glutamate will be negatively charged. And histidine, if you see the diagram I draw during the lecture, at pH 7, histidine will be neutral. Okay? So it means that if I draw the paper with the electrode here and here, so I remind you, histidine, glycine are neutral. So these two amino acids, both amino acids don't migrate. Glutamate is positively charged. Negatively charged. And lysine is positive. Okay, at pH 7. So it means that glutamate will migrate to the positively charged electrode, and lysine will migrate to the negatively charged electrode, and histidine and glycine don't migrate. Okay, so we have to depose the mixture here in the middle. And at the end, glutamate will be here, lysine on the other side, and histidine and glycine stay where we put the mixture. Okay, so this is at pH 7. You can do that for pH 1 and pH 11, it's okay?
Yes, that's okay.
Okay, I will give you a correction next week. Okay. Next exercise. So you have a peptide which is commonly present in cell and usually in bacteria, because it can have oxidoreduction walls. So he's called glutathione. Okay, you have the line formula here, and it's a tripeptide. So remember, a peptide bond, it's an oxygen, a double bond carbon oxygen linked to the amine group like this. Okay, so here we have two peptide bonds. This one and this one, right? It means that we have 3 amino acids. If we cut the peptide bond here, I'm sorry, here and here, you will have 3 amino acids. The first one, the second one, this one in green. I will put you in green. And the last one, okay? So you see that we start with the N side of the peptide. So it's this side. And here you have the C side. This is the convention. You always write peptide from the N side to the C side. Do you recognize peptides, amino acid? Here, you should know this one with the sial group. The one in black with the sial group. It's very important, I told you, with this group. This is
Is it a sulfate?
so what is the name of this amino acid?
Cysteine.
Yes, cysteine. Okay. This one, I will put another color. This one, okay, there is the carboxylate group, the amine group. There are no side change. This is the smallest amino acid. A very tiny amino acid. This is glycine.
Glycine.
Yes. And the last one. In blue. You have the carboxylate group here. The amino group here, and the side change. This is the side change with the carboxylate group. You have 2 amino acids with a side change contain a carboxylate group. This is glutamate or aspartate. Okay, here because this tripeptide is called glutathione, is glutamate. Okay, so if we give the composition of glutathione, it will be glu, cis, and G. Okay, the N side here, the C side here. So this tripeptide has redox activity. This is why you have a lot in mitochondria. Indeed, because you have cysteine groups, it can form disulfide bridge. So the glutathione, the abbreviation of glutathione is GSH because we put the sial groups, and 2 GSH can form a covalent bond called disulfide bridge, and it's an oxidation reaction. So you have here the reduce, it's called reduce glutathione, and this it's oxidized glutathione. Okay? Do you have any question? No. Okay. I think I will give you the correction of exercise 4, and after you will do as homework the exercise 5. Okay? I will give you in the slide, you will have the exercise. Okay? So here we have the mixture of 3 peptides, A, B, and C, which are separate using paper electrophoresis at pH 6.5. And you have the peptide. Okay? So first, at this pH 6.5, we need to know what is the charge of each peptide. Is it positively charged, neutral, or negatively charged? Because according to their charge, it will migrate to the anode or to the cathode. Okay? So for peptide 1, we have histidine is the N-side amino acid. So I will write the formula of this peptide at low pH, at acid medium. So for histidine, okay, you have the ring, aromatic ring, which is positively charged. Be careful, the acid group of histidine is not protonate anymore because it's involved in the peptide bond. After you have glycine with a so no charge. After that, you have choline. So it's a ring. And after you have lysine, which at low pH is protonate. Okay, so in these molecules, in this peptide, we have 4 peaky functions which can be protonate or deprotonate. We have this with a pKa at 9.33. This with a pKa of 6.4. Here you don't have any function which can be protonate, but the last one, the side change of the lysine has a pKa of 10.55 and the C side at 2.16. Okay, so if I draw a pH diagram, I will sort all the pKa. So here 2.16, after 6, 9.04, here 9.33, and at the end 10.55. Okay? At the low pH, I have a peptide which has 3 plus here, here, and here. So he has 3 plus. Okay? Each time the pH cross a PTA, the peptide lost a proton. So here you have only 2 plus. Here will be positive, minus 8 plus, neutral, and negatively charged. Did you understand what I made? Because it's very important. So I see which which group or function can be protonate or deprotonate. I can have the peaky value of each function from my table. I will always give you the value. You don't have to learn the value, okay? I will give you always a table. I draw a diagram, pH diagram, and I put the charge for the peptide in each region. Okay? Is that okay for you?
We need to remember the structure of amino acid, right?
You have to know that the first amino acid has the N, the amino group, and after I will give you in my table the structure of the side chain. So you don't have to know it. Okay?
Yeah.
But you have to know if it's positively charged, negatively charged, or neutral. So when you have nitrogen in the side chain, it can be positive or neutral. If you have oxygen, it can be neutral or negative. Okay? So I will do the peptide G with you, and as homework you will do the peptide C, okay? Okay. So peptide B, you have glutamate. So it's NH3 because it's an amino acid with a side chain of acid group. So it's blue. Okay. After that, you have leucine. Let's draw this. Sorry. Blue. After that, you have leucine. Leucine has a side chain which is neutral, which doesn't contain any ionized group. Okay, after that you have lysine. No, sorry, it's cysteine. Cysteine, you know there is a thiol group. After that you have aspartate at the end, because this is the last amino acid. You will have the carboxylate group and the side chain of the aspartate. I will put the pK value of each function. So this is 9.74, 47, sorry. Here 4.07, here 8.37, 3.19, and this 1 point. Okay? So in my pH diagram, I put the pKa in the order. At the beginning, at low pH, I have only the amine group which is positively charged. So I have 1 plus here. So it would be neutral in this region, and after minus, 2 minus, 3 minus, and 4 minus. Okay? If I want to determine the pI, I have the neutral form. So the pI of peptide A will be 9.33 plus 10 over 2. Okay? Here I have the neutral form of peptide B. So the pI of peptide B will be 1.9 over 2. Okay? So for my 2 peptide, you will do that the same for peptide C, but at pH 6.5, peptide A 6.5 will be positively charged. Peptide A positive at pH 6.5. And for peptide B, it will be here. So minus 2 minus. Okay, so next week you have to tell me what is the charge of peptide C at pH 6.5, and after you have to indicate the position of this peptide at the end of the experiment. Okay, and last exercise, the peptide backbone is flexible. In this example, it can fall to form ionic bond between charged amino acid. Okay. This peptide has variable conformation dependent on pH value. So with the help of the table indicating some pKa value, attribute one of this conformation of the peptide shown below at one of these pH value. Okay, you have 1, 2, 3, 4 pH value. You have 5 conformation. So you have to find me the pH of the last conformation. Okay. Can you do that for homework, or should I explain just this exercise for one peptide? We can have the correction next week. Is it okay?
Okay.
Okay, next week you have to do that as homework. So I have finished, or I can explain if you want. I can leave you. I can have lunch. Tell me what you want.
I think it's okay. We can do this, and we can try to do this, and you can explain to us next week.
Okay,
Is that okay?
so try. Yes, sure. Try to do that. And if you don't understand, I will explain. I will give you a correction next week. Okay?
Could you send us the note?
I will
This
send
note with
you.
the answer so we
Sure.
can
Right now. Yes. I have the email. I will send you right now, just after.
Thank you.
Okay. See you on Monday, Thursday next week. Bye.
See you. Goodbye. See you.
you